Welcome back to part 2 as I finish up the final example of double integration method. We are on page 15 of the note taker, and we've already cut the beam between 4 and 10 feet, and we've also cut the beam between 0 and 4 feet, and right now we are applying boundary and continuity conditions to get rid of our constants. We just set up the equation, the continuity condition, that states y at 4 feet from the left is equal to y at 4 feet from the right, which we've written out here. At this point we can then actually multiply through, cancel terms such as 1 over EI on both sides, and then simplify as much as possible. So we can simplify this equation to get 4c3 is equal to negative 56 plus 4c1 plus c2, and that gives us c3 is equal to negative 14 plus c1 plus c2 over 4. And again, that's as reduced as we can get this one equation. From here we need to go on to another continuity condition, which I'll slide on down to the top of the next page. We already identified that rotation at 4 feet from the left is equal to rotation at 4 feet from the right. And so from the left we had 1 over EI times 0.35x, which in this case is 4 squared, plus C3. And on the right side from our first cut we had 1 over EI times 0.35 times 4 squared minus 7 times x, which in this case is 4, plus C1. Setting these two things equal, we can say C3 is equal to C1 minus 28. And so we can say C1 minus 28 is then equal to negative 14 plus C1 plus C2 over 4 from above. Therefore, we can conclude C2 is negative 56. So far we've said C4 is 0 and C2 is negative 56. We still have C1 and C3 to determine. So let's go back to our first boundary condition from the first cut, which was y at 10 feet is 0. Recall we couldn't solve directly for any constant, but we were able to reduce it to negative 233 plus 10c1 plus c2 equals 0. Now that we have c2, let's plug that in. Negative 233 plus 10c1 minus 56 is 0, and therefore c1 is equal to 28.9. One more to go. Let's go back to our continuity condition dealing with vertical displacements, where we had y at 4 feet from the left is equal to y at 4 feet from the right. We left that one off with C3 is equal to negative 14 plus C1 plus C2 over 4. We know everything except for C3, so let's plug them in for C1 and C2. So C3 is equal to negative 14 plus 28.9 minus 56 over 4. Therefore, C3 is equal to 0.9. Now that we have all 4 constants from integration, we can finalize our equations. Now we really only need the equations valid between 4 and 10 feet because recall the problem asked us to solve for rotation and deflection at mid-span. However, since we went through the trouble of solving for all 4 constants, making 2 cuts, I'll just summarize all of our final equations here together. So for 0 to x to 4 feet, we have the following two equations. Rotation is equal to 1 over EI times 0.35 x squared plus 0.9. Deflection is equal to 1 over EI times the quantity 0.117 x cubed plus 0.9 x. From 4 feet to x to 10 feet, we have the following two final equations. Rotation in that region as a function of x is equal to 1 over EI times 0.35 x squared minus 7x plus 28.9, and deflection is equal to 1 over EI times the quantity 0.117 x cubed minus 3.5x squared plus 28.9 x minus 56. Now that we have the finalized equations with no unknown constants, we can plug in values for x and solve for what we're actually looking for. In this case, we're looking for rotation and deflection at 5 feet. Since 5 feet falls within this range, we're going to use these two equations and plug in 5 feet. Rotation at 5 feet is equal to 1 over EI times 0.35 times 5 squared minus 7 times 5 plus 28.9. Therefore, rotation at 5 feet is equal to 2.65 kip feet squared over EI. Now always remember that the numerator of any kind of rotation equation is always going to be in units of force times distance squared. That way, when we divide by EI, which EI is going to be in the same units, force times distance squared, the overall term will be unitless, which makes sense because rotation is unitless or radians. If interested, we could always convert to degrees later by multiplying by 180 over pi. We're also going to plug in y at 5 feet, and we get 1 over EI times 0.117 times 5 cubed minus 3.5 times 5 squared plus 28.9 times 5 minus 56. We do the math and we get y at 5 feet equals 15.6 kip feet cubed over EI. Now units, the numerator of this term, or any kind of deflection term, is going to be in units of force times distance cubed. That way when we divide by EI, we get simply a distance, which makes sense because deflection is going to be in terms of length. Since EI was actually given here in this problem, if you go back to the very beginning, it says EI is 15,000 kip inches squared. Let's go through and actually solve for a final number. So rotation at 5 feet is equal to 2.65 kip feet squared divided by 15,000 kip inches squared. We make the unit conversion by 12 inches per foot quantity squared, and we get rotation at 5 feet is equal to 0.0254 radians. Now we have a positive answer for rotation. Positive rotation is counterclockwise, so not only do I want you to have the right magnitude in units, but we need a direction. So a final answer here would be the rotation of 5 feet is equal to 0.0254 radians counterclockwise. If you choose to convert that to degrees, you'd find it to be 1.46 degrees counterclockwise. We're going to plug in EI for our deflection as well, and we would get deflection is equal to 15.6 kip feet cubed divided by 15,000 kip inches squared. We need to do unit conversions on that too. 12 inches per foot squared, and we get y at 5 feet is equal to 0.15 feet. Since it's a positive number, our direction is going to be up. We can leave it like that as a final answer, or if you prefer, we can convert to inches and you'd get 1.8 inches up. Either answer is correct. So the question said find rotation and deflection at midspan and also draw the deflected shape and label it. So the final thing we'll do is draw and label the deflected shape. The steps to drawing the deflected shape are draw your original beam, so we have a simply supported beam with a pin on the left and a roller on the right. We're going to label our point of interest, which in this case is 5 feet. And then we're going to draw our deflected shape. So the only thing we know about the deflected shape are the slope and rotation at midspan. So if we have a counterclockwise or positive rotation, we know that the angle is going to be something like this. If we have a upward deflection, we know that the point is going to be above its original undeformed location. So we know that slope and deflection come together to tell us that at that point this is the deflected shape at midspan. Now we just need to connect the dots to indicate the overall deflected shape. Even though we're only asked to draw and label the deflections at midspan, we still need to draw the entire beam's deflected shape and just label what the question asked for. So we have to apply what we know about supports. We know that at the supports we can't have any vertical deflection, but we can have rotation. So we're going to just extend this beam to meet the requirements of the supports. It's got to curve back down eventually, and it can't have rotation at the supports. So we know that is going to be the final shape of our beam, and hopefully that makes intuitive sense to you. Go back and see if that makes sense by just thinking about the original beam and that point moment. That point moment is causing is a counterclockwise point moment, and it makes sense that that would cause a deformed shape to be going diagonally up and to the right at midspan. So take a second to think about that and make sure it makes sense to you. Now that we've drawn the deflected shape, we need to label it. To label vertical deflection, we're going to be measuring the distance between the original undeformed shape and the final deformed shape and label it. So we'll say y is equal to 0.15 feet up, or if you prefer 1.8 inches up. Either one is fine. We've already labeled the distance below the beam, so just putting y is equal to 1.8 inches up is fine. For the rotation, from our point of interest, we draw a horizontal line to the right. In addition to that, we draw a tangent off of our deflected shape, also to the right. And that is how we measure the angle. And that is the angle we have to label. So we label that. Rotation at that point is equal to 0.0254 radians counterclockwise, or 1.46 degrees counterclockwise. This concludes our example. Please make sure you thoroughly understand how to do this and can replicate this for the GR. Good luck.